Okay, so let us continue where we left off last time. So we were talking about consistency. Let's talk about a whole slew of consistency, semantics, and models. And towards the end of the class, we were talking about this notion of eventual consistency. Eventual consistency basically means that there are very loose guarantees on how the replicas will be made consistent. The only guarantee is that any update that is made to any data item will eventually propagate to all of the replicas. Okay? There is no time specified on how long it will take or any of that. Okay? So it just says eventually the updates will propagate. And we talked a little bit about this notion of epidemic protocols as a way to implement eventual consistency. Epidemic protocols, as I said, were inspired by how diseases spread through pairwise contact. Okay, so if somebody is infected and they come into contact with another person, inadvertently they spread their infection, and then it sort of exponentially spreads until everyone, well, hopefully not everyone, but it becomes an epidemic. But in this case, we want to spread an update is equivalent to an infection. Okay, so there are many algorithms, as I was talking about. We will talk about two specific ones. The first one is called anti-entropy. In anti-entropy, it's a very simple protocol. A server P will pick another server Q at random. Okay? And they will make contact and then they will exchange updates. Okay? So every once in a while, a server will basically, so let's assume there are some number of replicas. Every once in a while, one replica contacts a randomly chosen replica in that set, and the two servers then exchange any updates saying, here are the writes I have seen, and now send me any updates you have seen, and they just exchange any updates. And the same thing keeps repeating pairwise. Okay? So you can send updates as a push only, pull only, or push and pull. A push only says that the server which initiated the contact is going to push its update but not ask for any updates. Okay? Pull only says that the server that initiated the contact asks the other server to give it any new information it has received, but won't push it. And you could, of course, have push and pull both operating at the same time. Okay? So this is basically anti-entropy. It's a very simple idea. It's fairly effective in many systems. And the idea has been used for lots of different ways you can synchronize. So if you have, let's say, a smartphone and you have a laptop, and let's say you have a shared calendar on both. Okay? You can make updates to your calendar on your desktop. You can make updates to your calendar on your phone. When you connect the phone to sync your phone with the laptop, this basically do pairwise synchronization. Okay? So that's basically push and pull. Very similar idea. It's using an epidemic protocol. In this case, the phone doesn't randomly choose to talk to your laptop. The user is explicitly initiating synchronization. But there are protocols that randomly and periodically go and initiate this synchronization over a network. But this is effectively what's happening there. Okay? Your calendar entries that have been updated on either the desktop or the laptop or any server, and the laptop gets synchronized. Okay. Now, the claim here is you could either use push or push and pull. And one claim that these kinds of protocols make is a push-only approach will not help spread the updates quickly. And then it's instructive to understand if you had this anti-entropy protocol and you're only using pushes to send updates to other replicas, why a push-only approach will not help the entire replica set to quickly get all of the updates. Okay, so think about how the push protocol works. Let's say there is a new entry that has been updated of some record. Okay? That machine will eventually decide to contact some other machine and push that update. Okay, now two machines have this update. Okay, those two machines will basically contact randomly some other machine and push, and it will keep spreading. Okay, eventually you'll have a scenario where some subset of the replicas have seen the update because it has spread, and some subset have not. Okay? And the claim is that once you get to that stage, pushing the updates to the last few replicas through a push-only approach is somewhat harder. Okay, is it clear why? Yes.
When you have the interrupt and you can't push it instantly, but you will be cost too many resources from the server, and you must have an interrupt and the packaging will be lost or something like that. So when you push it, so you can't push it instantly, but if you pull the server needs the machine and they pull the information and can use it immediately.
So we are not assuming anything about packet losses or anything like that. Okay, in this case, let's ignore all those complications that will make it even more complex. Okay, so let's think about how a push-only approach works. You can think of an analogy, right? Yes, you
It's the coupon filter problem, right? You randomly select a machine. If you have n machines and you're randomly selecting them, on average it takes like n log n tries to select all of them.
Right. So this is basically very simple probability or randomization. It's a randomized protocol. You're randomly choosing a server and pushing updates. Okay? After a while, when most of the servers have been infected and a small group is not, when you randomly toss a coin and pick, the probability that you will pick one server in the shrinking set keeps getting smaller. You will often select a server that has already seen that infection, maybe from some other server, and there is nothing to no data to update. Okay? So that's precisely why the probability that some replica never sees the update is small, but it is finite, and it gets harder and harder to push, because then you have to find the probability that that server is going to be chosen by some server that has already seen the infection, and that keeps shrinking. Okay, but if you combine pull with an initial push, then the probability will quickly drop, because every server is also initiating a pull. So it will. So as you have when you have a scenario where a majority of the servers have seen an update, but a small group have not, the probability that one of those servers in that small group pick some other server and then ask for updates is fairly high, because you will, if you toss a coin and pick a server, chances that you will pick an infected server is going to be much higher. Okay, and then you will pull that update and you will be done. You will get it. Okay, so think of how diseases spread. Okay, so you may actually go spread an infectious disease, and soon a large fraction of the class is, not a class, but a population is infected, but there may be a group that is not infected. Since you're not explicitly trying to infect someone, the probability that you'll pick, when you meet someone, pick somebody that's not infected will keep shrinking as the unaffected population also shrinks. But if that population goes explicitly looking for problems, like you want to get infected, then you can actually get infected quickly. Right? So if you don't take precautions, for instance. So same thing is true here. Okay, it's simply an artifact of how randomized protocols work. Okay, so that's anti-entropy. There's another protocol here which is called rumor mongering. Okay, this is also called gossiping, and this is why this entire class of epidemic protocols are also referred to as gossip-based protocols in the literature. Okay, so if you just do a Google search on gossip protocols, you'll see lots and lots of papers that have used some variant of these protocols. Okay, again, this is a randomized protocol. Okay, so what happens is whenever a server P receives an update, okay, it tries to push it. It randomly picks a server Q and tries to push it to the server. Now, if it finds that the server that it has chosen has already seen the update, it is going to toss a coin, and with probability 1 over k, it is going to stop pushing that update to all others. Okay? And if that Q has not seen that update, then it will continue. It will pick another server at random and try to push it, and so on. Okay? So the way to understand this protocol is how rumors spread. Okay, how you gossip. Okay, initially, if you have, let's say, a piece of news that you think is a hot news item, a gossip item that nobody has heard, you will actively go and start telling your friends, saying, "Look, I heard this." Okay, so but after a while, if you assume that people must have heard, you are not going to go actively do it. You just say, "I think everybody heard this by now, so I'm going to stop." Okay, the question is, how do you decide when to back off? So you back off when you get the impression that people have heard the rumor and it's no longer something that you should actively spread. The same thing is true here. So you basically keep pushing the update, and every time you encounter a server that has already seen that update, you toss a coin saying, "Is it time to stop? Because I'm finding servers that have already seen it." And with probability, and the coin toss will say yes or no, and you can tune the probability 1 over k depending on how aggressively you want to stop or how aggressively you want to keep spreading. So k is a tunable parameter in this protocol. But with probability 1 over k, let's say k equals to probability half, you may say you will stop. Okay, so half the time you will continue and half the time you will say I'm going to be done. Okay, so essentially, after a while, most servers will basically back off saying we are done. Okay? So what this does is it does not guarantee that all servers will receive the update. Okay, because each server is backing off with some probability and saying I'm done, I'm not going to spread this update. Maybe there are other updates it will try to spread, but not this one. Okay? So the chances of a replica never seeing an update is with this kind of randomized protocol, you can analyze it and show that it's sort of exponentially, an exponential function of k, and s, where s is the probability of staying uninfected. Okay, so as you by choosing k appropriately, okay, you can make that value become smaller and smaller. Because this is a randomized protocol, it is not going to guarantee to you that every server will or every replica will see an update. Probabilistically, there will be some small number of servers that will never see it. And how small, you can choose that value by picking the right value of k and tuning it. Is that clear? Yes.
So when do you stop the spreading in the first algorithm?
Okay, so there's a good question here. The question is, when do you stop spreading in the first algorithm? The first algorithm, you are not spreading a per data item update. These are pairwise exchanges. Server A and server B just connect and they say, what have you seen that I have not seen since we last talked to one another? And any new data is just there may be 100 records in one case and 20, you just exchange. Okay? This is basically, it's specific to a single update. Yeah, rumor mongering is not per server. So you decide on a per data item basis when do you stop. Here you are not looking at it on a per data item. It's just two servers just synchronize themselves. Okay.
Here is the queue fixed or like it changes?
Which
means in gossiping algorithm, means a particular P will only push an update to particular Q or?
No, so I think so P and Q are randomly chosen servers. So there are, let's say, n replicas, n servers. Okay. Each server, so let's say you inject a new data item X or a new update X. Okay, so this server will randomly choose another server and try to push. Okay. And then each server will repeat. Now both of these now have X, so they will repeat. They will randomly choose another server and keep spreading. Okay. And once a server encounters another server that's already seen X, they will toss a coin saying, this server has already seen the rumor. Should I stop or not? Okay, that's basically what that tossing a coin probability 1 over k does for you. Okay, so these are just pairwise exchanges where the two servers are randomly chosen among them. They just choose each other and they try to spread. Is that clear? Okay. Any other questions on epidemic protocol? So these are two very simple versions of class of epidemic protocol. There are lots and lots of them, but the basic idea should be clear as to how it works. And what we are trying to achieve is essentially eventual consistency. Any update that you have made will eventually propagate to all the replicas. There are no guarantees on when that happens. That's why it's eventual. Over some long period of time, they will converge, but no guarantees are made.
Means here you are saying that means if the other server has already seen the update, then this server need not update the server because other server has already seen that. So means why it needs to stop there? Means is it the case that the one server is contacting many servers to push its update or?
So the analogy is how gossip spreads, right? So just to understand how this is going to work, let's say when you get a new data item that's equivalent to somebody in the group found some hot item that they want to sort of gossip item they want to spread. So they will basically start telling their friends will start telling their friends. That's how gossip spreads, right? So the first server will contact us and some server spread it. Now these two servers have this gossip item, they will contact some other server, spread it. Now if 4 of them have it, they will randomly choose others in the pool and keep spreading. So the gossip will quickly spread to several of the servers in the group. And since you're randomly, each server continues to do this. Just because the server did it once doesn't mean it stops. It will continue. Each server will continue. So you need a way to say when to stop. Okay, so that's basically when you say, if you encounter, you pick up server at random and you have to push it and you find that it has it, you stop. Okay. Alright, so that's epidemic protocols. Now, one problem with epidemic protocols that is worth mentioning is how do you delete a data item? Okay? When you update a data item, whether it's a file, whether you have updated a calendar entry or whatever it might be, okay, spreading that is easy, but deletions are not trivial. Okay, so if you delete a data item, then you may see that there are some problems with the protocol. So let's assume that there is a record in the database, okay, that you basically just delete. Okay, you delete it at one replica. Okay, so now I just remove it. Let's say it just removed it. Now if that replica actually goes and contacts another replica and say, or that replica gets contacted by another replica and says, do you have X? Okay, and you find that since it's been deleted, that the item is gone, it doesn't have X, it will be actually given that X again by some other machine that has the undeleted version of the data item. So your data item has magically reappeared, even though it was deleted. Right? Yes, question.
We could track like the ID of an update, not its effect. Right?
Come again.
Like X could have said, "Oh, I've seen this message already, and I, updated that deleted data item already before it was." I don't know.
Yes. So I think some point I'm trying to make is if deletion means you actually remove it. Let's say it's a calendar entry. I mean, let's make it explicit. You have your phone, you have your desktop, and your shared calendar. Okay? You put an appointment on one, and let's say it gets propagated to the others. Now both are in sync. Okay? And you decide that you want to cancel this meeting, you delete it from the phone. Okay? If the phone actually removes all trace of that this calendar entry ever existed, and the next time it synchronizes with the desktop, they will push anything that the phone doesn't have will get pushed back again. Okay? And that calendar entry will reappear. Okay?
So the thing I'm missing there, I think, is that we don't have an ordering on updates.
Yeah, so you do not have, well, it's not just, yes, if you update, let's distinguish between update, which is a write, with a delete. Okay, delete is a form of update where you just remove the data item. When you remove, if you actually remove all traces of it, that's a problem. Okay? Rather, what you should do is you should keep the data item, but then mark it deleted. Okay? This is referred to as a death certificate. Okay? So you don't actually delete that calendar entry. You just keep it, but mark it deleted. So next time when you synchronize, you will actually track it as an update rather than you have taken it out from the system and it reappears. Okay? So it is simply a new update that you have made by just marking that as deleted. Okay? Only if you do this will this work. Otherwise, if you do pairwise exchange, you say what is it that you don't have, you will just basically get deleted items will suddenly start reappearing because you just removed them. You have no idea you removed them, they will just reappear. Okay, yes.
But it won't be true in the rumor mongering case. In the rumor mongering case, if you just propagate deletes, how you do because you're not doing pairwise synchronization.
If delete simply means I remove it, okay, then that's not true.
And if I just pass along that delete message to all the other servers in the pool.
Right. Typically, the way things work is, let's say read, write, delete. They just arrive at a replica. You perform the operation. You don't actually propagate that, and then you look at the state, and then you just do pairwise exchange. Right. So let's take a very simple example because if this is not clear. Let's say you have a directory, okay, and it has some files, okay, and you are trying to keep them synchronized by rsync. Okay. This is an example of epidemic protocol. Periodically, you write a cron job where you take this directory and you rsync them. You say, you send me any files I don't have, and I'll send you any files that you don't have. So these two directories are in sync. Okay. If you simply did this, and let's say you now deleted a file out of this directory when they were synchronized, next time you rsync, if that file is still there, it will basically get sent over because you are doing two-way synchronization. Okay, because if you just actually removed any entry of the file, this will look like a directory with only one file. this has a directory with two files A and B, and you rsync, then this will reappear. Okay, that's basically the problem you're trying to avoid. So what you want is not to actually delete it, but keep the file, but mark it deleted. Okay. So that will simply look like a updated version of the file. So then you'll propagate that file and also have the delete mark appear on the other file. Okay. So in some sense, you don't actually propagate the requests themselves. You propagate, you're synchronizing the state. This is how most of the systems will work. This is what also calendars, with shared calendars, all of them work the same way. They don't say that a new entry has appeared. They just look at the state and compare. They don't see what has actually happened. Okay. So updates have to be spread. Deletions have to be spread as updates essentially. Why that certificate you mark a copy is deleted, but don't delete. But then eventually you want to do a cleanup because there will be a lot of old files that have been deleted where the state still appears. So you need a way to clean them up. There are ways to do it which we will ignore here for now. Okay. So that's basically all that we have to say about epidemic protocols. Okay, as I was saying, they are widely used, whether you use source code control, if you have used any source repositories, Git or SVN, all of them essentially work on the principle of eventual consistency. You update, let's say there's a source repository, you update a file, okay, and then others will eventually pull that file from that. So you are either doing pushes or pulls. You push your updates to the repository, and you pull updates from the repository, and then your copy, in that case there is a master, so you update with respect to a master, but you don't need to have that master. You can do pairwise updates as well, just as you can do in Git. In Git there you don't need a master, you can have any copy synchronized with any other copy by doing pushes and pulls. So these ideas are now actually widely used in variety of different contexts, whether it is synchronizing calendars, whether it is using source code control repositories, or many other types of synchronization based systems. Okay, so I'll talk a little bit about implementation. We have covered quite a bit of ground on consistency, semantics, and models, but haven't said much about implementation at all. We're going to talk very quickly about some easy ways to implement variety of different semantics. Okay? But we'll not go into details of how to implement each one, okay? But just sort of give high-level ideas. So there are two ways you can implement a consistency protocol. Okay? One is in which one we'll call primary based, and the other is replicated. Right? Basically, it depends on whether do you have a coordinator or a master, or there is no coordinator in the system. If there's a coordinator, then all updates go to the coordinator, and the coordinator's job to propagate that update to all replicas. If there's no coordinator, then all replicas have to participate and determine how updates spread. Okay, two very broad classes. Okay. So the primary based is one where there is a primary replica for each data item, and the replicated one doesn't have any such replica. Okay. So let's look at the idea behind each. When we come back and talk about distributed file system, you'll see that these ideas map directly into how NFS and lots of other network file systems actually implement writes for files and so on. Okay, very sort of direct mapping. So this is a primary based protocol. Okay, so what happens in a primary based protocol is essentially there is a master for each file. All reads and writes have to essentially go to that, not all reads and writes, all writes have to go to that master, and the master will propagate that write to all other machines. Okay, so all other replicas. So here you have a client that has issued a write. The server or the master is this one. Okay? So the write comes here, and because you have to essentially involve the master, you forward the write here. The write is actually performed here, and you get back an acknowledgement. Okay? In this case, if there is only one copy of the data item, even the read requests have to actually be forwarded. Okay? So in this case, the read comes from the client here. This replica does not have a copy of that data item, so it's going to forward the read. Okay? Now, if there are multiple copies, then reads can be performed locally. Okay? So I'll show you that example on the next slide. So here is a case where that's the primary, okay, but there is a replica of that data item. Okay, this is the master copy of a file, let's say. There's a replicated copy of that file here. Okay, And same scenario is true. Initially a write comes in, write is sent to the master. The master performs the write, but now it has to send an updated version to all the replicas, saying the file has been updated, here is the new version of the file. Okay? So you will see that there are messages actually going back and forth to all. So this W3 message is actually going to every copy, saying here is the new version of the file. That's called sending an update. Okay? So you propagate the update. So every replica now has a more recent version of the file. Okay? So that's what the master's job is. Whenever it sees a new update, it has to actually send it to all replicas that are present in that file system. Okay, in this case, reads are performed locally. When a read request comes in, if the replicated version of the file, you just return the results of the read. Okay, you don't have to check with the master because master is already propagating all of the updates. Okay. This is going to implement sequential consistency that we were talking about last time. Okay. Very simple idea. Updates come in, updates are sent to the master, which coordinates the write. It performs it locally and it tells all the replicas saying here's a new version of the file. Okay. So this is the local write protocols are an optimization where you still have a master, but the master is not statically determined, it changes dynamically. Okay? Which machine is the master will change on the fly, depending on where the reads and writes are actually happening. Okay? So the scenario here is that initially this machine here, the disk shown here, is the master for the file. Okay? If a client makes a request or wants to write to the file, then when the write request comes in, it sends that write request to the master. The master says, here, take over this file instead of sending it to me. And it sends it the file and that machine becomes the new master. And so once it has become the new master, all the writes are actually going to be local. You don't have to actually send them to the master. So you can just send them to the local machine. And so can reads can also be done to the local. Now we will see when we talk about NFS. In particular, NFS version 4 uses this notion. Okay, this is often referred to as delegation. So you are the master, but if there is some client that is actively reading and writing the file, you can temporarily delegate responsibility to that machine so that all I/O requests are local for performance reasons. This is only a performance optimization. Right? It is just reducing the number of messages that have to be sent. You could have kept the master where it is, and then all writes would still have to be funneled to that machine. If all the writes are happening on this first machine, then why not make delegate responsibility and make this machine the new server so that the writes are actually going to be low. Now, if there are lots of replicas on this file, giving that responsibility to that machine doesn't actually help, right? Because that machine still has to notify all the other replicas and it still has to send those messages. So in scenarios where the replication is dynamic, where the number of copies of a file or whatever data item that are present in the system is dynamically determined based on the popularity of the file, these kinds of protocols make sense. When there are small number of copies or only one copy, you can actually delegate responsibility. There are lots of copies, somebody still has to do the work of notifying all the replicas. So there is not much to be gained by saying you take over, because that other machine still has to do all that extra work of notifying. Just as we saw here, there was this server had to notify this machine, this machine, this machine. So all those messages still have to go out. So just handing responsibility to some other machine doesn't actually save you that much. Okay? And when we talk about NFS, we'll see it's intelligent. It will delegate responsibility only when there is a single writer in the system and single copy. There are lots of copies floating around, it will not do that. It will stay as the server master and it will do all the job. Okay? So some of these ideas are actually, you will see, actually used in real systems in various shapes and forms. Any question? Yes.
In the previous figure, how do you prevent cyclical, requests going back and forth between a master and a copy? For example, if W1 came in, then W1, that copy propagates the request to the master, and then the master will send back a request. That write request is the same as the write request that came in from the client. So how will...
Okay, so question is, how do you prevent cycles where if a write request came in, you send that to the master send the write request back to other machine? That's your question, right? So just as I was talking about in Epidemic Protocol, you have to distinguish between the original request and an update. They are two different things. Okay? What comes into the system is a client request saying write to this file. That's an explicit write command or a write request. Or as a shared calendar, you actually go and you create a new calendar entry. That's a write that you made. Okay? What goes out are actually updates, not the original write request. Okay? So for instance, what might go out, you may write to a file, you may add one line to a file, let's say. What will go out is actually the new version of the file. You will actually send that new file over. So you are not sending the write request and saying go perform this write. Okay, that's not what is actually happening. You are sending the results of the write, which is the new version of the file. Okay, so that is not, yes, your question. Yeah, go ahead.
Okay. This is a minor point. And is W5 acknowledging that the write has happened on at least one replica?
W5 is essentially saying that write has completed in the system. The semantics of what that means is actually going to be dependent on the system. Okay, so this is basically, let's say this is a client that just opened a file. You do fopen in C, or basically let's say you open it in Java and you write to the file. Okay, when basically the fopen returns is what when W5 comes back is when fopen will return. So until then, fopen will be blocked, saying the write is in progress. Okay. Now, if it's a replicated system, the system designer will tell you what it means when the write returns. Okay? In some cases, it may mean that the write has only reached the master and the master has performed the write. In some cases, it may mean that not only has the master performed the write has propagated to all machines in the system. Okay? That's the semantic of what a return of a write would mean. That would be very much dependent on the system. In this case, just to answer your question, in this case, given these steps, a write return requesting W5 essentially is an acknowledgement that your write has finished. In this case, it actually means that the write has propagated to the master. The master has committed the write, meaning it has actually performed the write on its copy. It has sent that copy to all the other machines, and all other machines have been updated. That's what a return of a write typically, in this case, is what it would mean. That's actually going to be a fairly strict definition of what write will. Typically, systems will not wait that long. Yes.
Sure. So maybe I'm reading too much in the picture, but there's no response from the master that all the acknowledgements of that receives. There's no like with what you've described, I would imagine that
you would actually have to wait for the master to actually say that all. What is not shown is acknowledgements from all the replicas saying to this W3 message, right? So W3 is saying that tell backups to update. We have not actually said that you will basically get that. You're right about that. So you do acknowledge the update. I think you should have explained. There should have been a final message there. You're right that you have acknowledged that all replicas are acknowledged. Right, so that's not shown in the picture. It's taken directly from the book, but that's the semantics of what we are actually saying. So you wait, you send all the updates, you wait for the acknowledgement, and then you send back. And so that acknowledgement is that there is a W4 that each of the things have actually each of the replicas are acknowledged, but it doesn't say that W5 is actually happening after W4 and there's explicit message. That is not shown, but that has to happen in this case. You're right.
So,
Very good point. Yes.
in this case, the semantic, the way the picture is drawn, it would mean that only the replica on which the write is performed, when that gets committed, then the client is getting an acknowledgement. In this case, then.
No, so that's not what this figure is showing. So what you are saying is basically what is called write back caches. That's what write back caches do. Write comes in, you perform the write locally, and then you return. It is not propagated to anybody else. Okay. That basically all that it says is the local machine has received the write. Whether when it is going to propagate, all that is not defined in those semantics. This is a much stricter semantic. This is saying that the write has been received, it has been sent to the master. The master has performed the write. It sent an update to all replicas. All the replicas have also committed their version. They have sent acknowledgements, and now you are getting back. So that the write has propagated to all machines. That's what it means. So everybody has seen the write. This is what this protocol will do. What you are asking is a much simpler case where You only do it locally and then you return. Okay, then asynchronously the write gets propagated. So that's not what is happening here. Okay.
You said that with strict consistency is like difficult to implement, but isn't it the case that with the master in the system, is it maybe possible to implement strict consistency?
Okay, so I did say strict consistency is difficult to implement, okay, but it's not impossible. We will hold back on how to implement strict forms of consistency when we talk about the web, because it will be much easier to understand. There are some simple methods to figure that out. Okay? Now, you do have a master. Okay, so now the reason this is, I said it's sequentially consistent and not strict consistent is the following. This write may be in progress and a read may actually come in, but just after the write has arrived. So now there is, unless this replica is actually going to first check whether the write, any write has actually just been received, you cannot implement strict consistency. If you just assume that whenever updates come in, the server will send them to me. But then I'm going to, whenever read comes in, I'm just going to take my local copy and return. That can only be sequentially consistent, because you may have just received that read request just after write has been received here, but there are finite propagation delays here. It's not going to be that these messages will instantaneously propagate. So you cannot say that this is strict consistent. So even though you may have a master, when the master is immediately updating all the server, all the replicas, there's still going to be a finite lag between when the write is received and when all the replicas have been notified. Right? Any reads that arrive in the interim might see a stale version of the file. Okay? And that's okay for sequential consistency, not for strict consistency.
I mean, even for sequential consistency, we need to assume that first in, first out messages are going.
Yes, so there's in ordering and all of that. Because you are ordering all the writes at the master, the order is determined by when any write request has been received by the master, and that's the order in which it's sending out notification. That's the only reason it is sequentially consistent, because the master is simply ordering them. Yeah, otherwise it would be even harder to do this. Yeah, any other questions on this? Okay, so local writes are, as I said, fairly straightforward. You're just delegating responsibility for the master. The master for a file keeps hopping around depending on where the action is, where the I/O is happening. Okay? And this works well for mostly if you are single writers in the system, that there's one process that is actively reading or writing. If there are multiple writers to the same file or same data item, there's no point delegating master, because there will be multiple copies and you would have to propagate those writes. Okay? So this only works as a heuristic in the scenario where there is a single writer. Okay. Now this is a more complicated version of the same picture on the previous case, where there are multiple replicas. So here is the original server. There's a client there, let's say, that opened that file and started writing to it. So this server said, here, take over the file. So this has become the new server. Okay? So each write that comes in, right, if there are multiple replicas of this is the master, but there may be slave copies. So every write that comes in still has to be sent to all of the other machines, and that is basically what is happening here. Write comes in, it is being W4 messages are going to all the other replicas. Acknowledgement, W5 acknowledgements come back, and that basically tells the server that the write is finished. Okay, so that's basically, and here you will see that the write request returns right after you only copied it to the local machine. You are not even waiting for all the other replicas to acknowledge. Okay, so write comes in, okay, you take over the file, you perform the write, and the client basically is told that the write has finished. Because it's local write, you're not waiting, and then asynchronously after the write has finished, you're sending all the updates. Okay? So this is going to be even more loose than sequential, okay? Because you are sort of asynchronous from a consistency standpoint. You are not waiting for all our replicas to be notified before the client is told the write has completed. Okay, is that clear? So, although this is more of a distributed system scenario, there are similar analogies to keep in mind even when you have a centralized single machine file system. Okay? So in Unix, if you open a file and you write to it and then you close the file, okay, Unix actually does not guarantee that the file has been committed on disk, because it can actually perform that write in memory. Okay, and you're basically the I/O may not have been committed. I/O is committed asynchronously. Only if you flush your memory buffers are the writes actually sent to disk. So in that case, you can think there are two copies of the file, one in memory and one on disk. Okay, writes are coming and are updating the memory copy. The disk, those copies are being asynchronously propagated to disk. Okay, so when your write request finishes, you cannot assume that the file has been updated on disk. In fact, often after the write request finishes, if your machine crashes, okay, that write would not be seen on disk. When you recover or restart, you will see that the file update has been lost, even though the write had technically returned to the client. Okay. So, and that's simply because there are different semantics on consistency. Unix is not guaranteeing you, in this case, that it's a write through. If it's write through, then you have to wait for that write to propagate to the disk before you return, just as we saw in the remote write case. Okay, what you'll get is something similar to this, that locally the write has finished in memory, but it hasn't propagated to the other copy. Okay. Now, all of this discussion we have had so far has focused on what we call primary write. There is one master. Whether the master is static or is moving around doesn't matter, but there is still one master and there is a coordinator. Okay. We will now look at another version of this protocol where there is no master at all. All replicas have to coordinate on deciding how to commit the writes, and whenever a read request comes in, which version to return and so on. Okay. So we are going to relax the assumption of a primary. There is no primary. Writes can come to any replicas and they can make update those replicas, and we still want some consistency. Okay. Now this class of protocols that we are going to look at now are broadly referred to as quorum-based protocols. They are based on the concept of voting. Okay. Replicas will vote to determine what is the most recent version of the file. Okay, we'll impose some constraints on how reads and writes work. Okay, and replicas would have to vote, and only when they agree will a read or write actually finish successfully, as we'll see. Okay. So you use voting to determine what to do, and here is essentially how it is going to work. Given any, let's say there are n servers, and a file is replicated on all n servers. Okay. Whenever a write comes in, okay, you need to update at least n over 2 plus 1, strictly greater than half the servers, before the write finishes. Okay, let's say you issue a write request that to your local machine, which is one of the replica. That local machine has to ensure that that write has actually gone to at least these many servers. Okay. That is referred to as the write quorum. That's the number of machines that have to have seen the write. Okay. Now, when a read comes in, you are going to contact a read quorum that we will determine. And you basically get the version number of the file. You ask each machine saying, what is the version of the file you have? If they all agree that I have version 71 or whatever the version number is, so you'll assume that with each write there is a version number that you will increment. So you know what version of the file it is. Okay, you could have done the same thing with timestamp. Timestamp is also one form of a version number, but since clocks are not synchronized, we use a logical integer as a version number. So when you read, contact a read quorum. You ask for version number. If the version numbers match, then you take any one file from that replica and you return. Okay, you perform the read. Okay. So there is a notion of a read quorum and a write quorum. A write quorum says that you have to at least contact NW servers to perform the write. A read quorum says you have to contact NR servers. Okay. And this is how you choose the size of the group. Okay. So you want the write quorum to be strictly greater than half the number of servers. Strictly greater, and NR plus NW has to be greater than N. And that's how you pick. So once you've chosen the right quorum, then you can pick the read quorum using this constraint. And let me show you an example to illustrate what this all is doing for us. Okay, so here we have 12 servers, A through N. Okay, there are 3 different examples of how you have configured this protocol. This is referred to as Gifford's quorum-based protocol. In the first case, the write quorum is set to 10, the read quorum is set to 3. What that means is every write that comes in has to be sent to 10 machines, 10 randomly chosen machines in this pool. It doesn't matter which 10. Pick 10 and send the write to those machines. Every write has to be sent to 10 servers. For read, you pick 3 servers at random, and if those 3 servers agree that this is the latest version number, then you return that. And if they disagree, then pick another 3 servers until you find 3 servers that agree. Okay, this is why they are voting. They keep voting until you find 3 that agree, and then once they agree, you are guaranteed that that's the latest version of the file. Okay? And here is an example to show what happens. So what is in the dotted group is a write quorum of 10. Okay, let's say you update a file, you write to a file, and that has been seen by C through L. Okay, now let's say you try to read that file. You have to pick 3 servers at random. Initially, let's say you pick A, B, and C. Note that A and B never saw the original update. Okay? So you will ask A, what is the version of this file you have? What's the version and what's the version? C has the latest version. So A and B's version number will not agree with C's version number, because A and B did not see the file. So you will say that these replicas disagree, so I cannot perform the read, I have to repeat. So you pick 3 other servers. Okay, so let's say now if you pick E, F, and G, just out randomly, then they will agree, because they all saw the write, so they have the same version. If they agree, then you are guaranteed that that's the most recent version. Okay? And the claim is, because you have chosen the read quorum and the write quorum using this formula, there is no way you will actually have your read quorum or ever return your old version of the file. Okay? If you had mistakenly set NR to 2, let's say. Okay? If you had set that to 2, you could have picked A and B. A and B might agree, and then you would actually return an old version of the file. Okay? Because you have chosen it such that simply because NR plus NW is greater than N, there is no way to pick some number of read servers which does not overlap with at least one server in the write group from the previous write. Okay? So you will always find at least one server that has seen the most recent write, and it will disagree with the rest and force you to keep doing this until you find all servers that agree. Yes, question.
Isn't there still like a time delay between when the write messages gets propagated? So you could do the read before C actually sees the write message. Then A, B, and C will agree, and the write will still complete.
Okay. So question is, there is some finite time before the write message is propagating, right? So the read message can come in, and while the write is still propagating, and C may not have seen it, and A, B, and C will agree and return. That is okay, because just by the way things have been defined, you will assume that read has actually executed before the write that is still in progress. Because the write is in progress, it hasn't completed yet. Only after it has completed can you say that any subsequent reads should see the request of the write. So in this case, they are concurrent, so the read is actually finishing first, and it just picked up the old version. That's okay. Because this is a distributed system. We don't have a global clock, so we don't exactly know in what order that has happened. This is a write in progress. Yes.
So you mentioned that since NR plus NW is greater than N, then you always get the newest version when you read. But why do you need the second inequality?
Okay. That's coming next. You are asking a good question, saying, I explained to you why NR plus NW needs to be greater than N. Okay, because I said, if you don't have that condition, if NR was 2, you might pick accidentally some servers that in the read quorum that have not seen it. So you want to pick it this way such that NR is also always going to overlap with at least one server. And the question is, why do you need this? Okay, so here's an example to show you why NW needs to be strictly greater than half. So we have chosen NW to be 6 out of 12. That's not strictly greater than half. That's exactly half. Because strictly greater means it has to be at least 7. So now you can see what happens. Okay, so, and we have still picked NR plus NW greater than 12, so NR has been set to 7. Okay, the first equation is still satisfied. NR plus NW is greater than 12, but the second one is not. Okay, so here you pick, whenever a write comes in, pick 6 servers and perform the write. Okay, so that's the dotted group. You pick this dotted group and to perform the write there. Okay, now your read comes in. Okay, you have to pick 7 servers that agree. Right? Now you will see that this read will never succeed because this other A to G have not seen that write. So you will always pick at least one server from this pool. Because you may pick, in the worst case, you will pick 6 of these and you will pick one of those. Or you may pick all 6 of these and you will pick one of the old ones. So there is no way to pick 7 servers that have all chosen, that all agree. So you will never have reads succeeding. They will keep trying and keep failing. Okay? So this should clearly tell you that NR has to be at least smaller than NW, and NW has to be at least half because you want majority to agree. Okay, there is a majority rule. Okay, yes, question.
Why should all the NRs agree on something? Suppose in the first case you have A, B, and C.
Yes.
If A and B have an ID of 71 and C has an ID of 72, you know that C is the latest one. So you can just propagate that.
Okay. Question is, why should NR groups in NR agree? If you actually could go and compare the version numbers, you know that C actually has the latest version number. So the question is, not the question, the reason is, you don't know who has the latest version. You are just randomly, writes are appearing randomly into the system, you randomly pick some group, and those are the only machines that have seen the write and others have not seen the write. So how do you know C is the one to actually check and that has the write? Only way you can do is ask everyone. That's the simplest thing. You always, when a read comes in, if you set the read quorum to be n, this will work. You will always ask all of you, what version do you have? This will say 71, 71, that is 72. So you poll everyone, you get, say, this machine has the latest one, and then you are done. Okay. But the overhead of asking everyone is very high. So you want reads to ask as few as possible to reduce the overhead. Okay. The only way you will find what is the most recent is you have to ask every server in the system, because only some servers are randomly seen.
Yeah, but only C is part of the write quorum, right? So once C updates, we know that.
Who is V? Let's say a read comes in. Okay, I give to you have 12 servers. A read has come in. Which machine are you going to ask?
We know that one of them will overlap at least, right?
Yes.
One of them will overlap between the read quorum.
Correct. That's exactly the point. That if one of them overlaps. So what is your question? That you don't need to keep asking? Is that the question?
Yeah. So one of them overlaps.
Yes.
So we know that one of them the timestamp will be greater than the other.
Yes. So you could basically ask. So you are simply proposing an optimization where I said if they don't agree, keep retrying until they all agree. Right. So you are proposing an optimization saying you just pick any NR. And from that you pick the most recent version number and ask. So that will also work because that will always give you the most recent number. Yes, now I understand the point. So you could always just ask NR servers here and ask them for the version number, pick the most recent because you know the most recent one is part of the write quorum. That would be true.
But what
Yes.
happens if another write comes into A this time? Now A has the version of the file that is 71. Now it has to propagate the write request of, let's say, 10 other, like 10 randomly chosen servers. How does it propagate the write after that? What version number again choose the maximum version number?
Right. So question is when a new write comes in and you now hit a server that had not previously seen the update, what happens? How does it all work? Right? So this protocol is only talking about how the voting part of it works. Okay? So there has to be something else that is actually propagating the writes and bringing them to consistent state, because eventually that write does have to propagate here. Although initially the write has only been seen by this. If they don't see it, then you may have files where you've never seen the write, a new write comes in. Okay, you can't just perform the write on some stale version. You always have to perform. So that part is left aside. This is just telling you how the voting part of it works. That this is how you can ensure that by simply having version number and simply voting, you will never go wrong. That's all it is saying. There has to be still a way by which you will actually propagate the updates and so on. That is left to the implementation. The protocol is just about how do you ensure that there is a quorum. Okay. So the last, so this hopefully is clear why there has to be at least a majority right. Otherwise, you will always block. Okay. The last case is basically a scenario where you only want to ask one server for a read, and you want to be guaranteed that the server has the most recent copy. You want the read quorum to be 1. I never want to ask more than one server. You can always set the read quorum to 1. Okay, but then for the read quorum to be 1, the write quorum has to be the entire group. Yeah, otherwise you can never do this. So if you set NR to 1, then NW has to be N. Okay. If you do this, then basically it says every write goes and hits all servers. Then all writes, all reads are always local because everyone has the most recent version. Okay, so this is also referred to as read once, write any. I think this is chopped up. Yeah, so you basically only write all, read one. I mean, you write to everyone. That means all reads are always local. You don't have to do any voting. Everybody is guaranteed to have. So what Gifford protocol allows you to do is you can pick how you want to set NR and NW that will basically have different overheads on performing reads and writes. Right? Here writes are very cheap, reads are the most expensive. This is somewhere in between. You have to ask at least 3 machines. There's some more overhead than this, but writes are somewhat cheaper and so on. Okay, is that clear? So this is basically core. These are called quorum-based protocol. They all use this concept of voting. Okay? This concept of voting is probably the first time we have encountered it here. But again, it is a very common principle in distributed system. Okay, there are a class of protocols called consensus protocol. Okay, where they all have to vote and agree. Okay? And depending on what they agree, you can basically do something. Okay? So consensus-based protocols also use the similar concept of voting. When we talk about fault tolerance shortly, you will see again voting does play a part in that. Okay? Because if you have multiple replicas and some of them are faulty, they all have to vote and decide what's the right answer. Okay? So this notion of voting, as we'll see, is another of those general ideas. This is the first time we have encountered it. Okay. Now there are some issues with respect to replica management, which we will come back to when we look at the web. Okay, this is just a placeholder slide to say I only talked about replication protocols, but when I started the lecture, I said there are many questions to answer. How many copies to keep, where to put them if it's geo-replication, how to deal with consistency, at least we saw. But how do you decide how many replicas are the right one? All of those are important questions one has to answer. But we will defer that discussion. We'll talk about it in a very specific context of the web and web servers and web proxies. Okay. So just to wrap up, replication, as we said, has two. We do it for 2 reasons: either to get scalability or to ensure reliability. Okay, you replicate, so if machines go down, there are other machines that are still have a copy of that data or computation. Or if machines get overloaded, you replicate, so you have more machines to service the incoming workload. Okay, so those are 2 reasons, and the main issue you have to deal with whenever you do replication is how to ensure all copies are consistent. Okay, so we spent these 2 classes talking about consistency models. We have covered a whole slew of them. Okay. There is a whole bunch starting from strong to weak. Okay. We'll see that most real practical systems somehow deal with weak consistency. Strong consistency is always hard to achieve. Either it's either expensive or in some cases we'll see that it's not possible to achieve. So most systems we'll encounter as we go along, we'll look at several. They all use some form of weak consistency, including in the web, which we will look at when we do the web chapter. Okay, so I'm going to stop as far as replication is concerned, spend a few minutes introducing the next chapter, which is on fault tolerance. Okay, is there any question on replication before I continue? Okay, so again, the last lab, incidentally, the second lab I put up yesterday. It is going to be due much after the midterm, so you don't have to worry. But I do want you to take a look at it and think about it. Lab 2 requires you to think about logical clocks and leader election, some of those things that we talked about. The last lab is going to ask you to think about replication and fault tolerance, saying what happens if machines or pigs or whatever go down, or you want to get performance, you replicate some state and things like that. So all of this concept you will implement in a toy form. Okay, the applications we are looking at in the lab are really toy applications, but they illustrate the principles. Okay, so you will have some more thinking to do when you design the lab as far as replication and fault tolerance is concerned. Okay, so let's continue and switch gears to the next chapter, which is fault tolerance. So single machine systems. Okay, so the thing to keep in mind is machines fail. Software has bugs, software can crash, hardware parts can fail, or there may be actually hardware bugs. So there will be faults in any system. Okay, in single machine centralized system, if the machine fails, everything stops. Okay, the application just stops functioning. Luckily for us, in a distributed system, when independent components fail, the application as a whole does not have to stop. Okay, because we can leverage replication, other components can take over the responsibility of the failed components, and the system as a whole can continue to function. Okay? Now, the question that we want to basically ask really is what kind of mechanisms to employ so that this can be done automatically without human intervention. You don't want some administrator to say, that server failed, I have another copy there, so I'm going to do some reconfiguration and now that server will take over. This has to be automatic. Okay, the replicas have to detect that some machines have failed. They have to reconfigure themselves so anything that was being done by that replica is taken over and things just continue seamlessly. If you build your system well, you will not, your users will never see that the components are failing. Yeah. In fact, the reason you want to actually think about fault tolerance is in large distributed systems, failure is the common case. It's not an exception. In a centralized system, you will assume that your machine rarely fails. Once in a while it may fail and you have to deal with it. But in a distributed system, failure is going to be the common case. And the simple argument for why that is the case is very straightforward. It basically says if there are n components in the system and p is the probability that any component fails, and let's say components fail independently, then the probability that there is any component has failed is 1 minus p to the power n. Okay. Okay. For any p, think about what happens as the number of components grows. As you have more and more machines, n is the number of machines in the system. P is the probability that one machine can fail. Let's say machine can fail once every 5 years. But you have lots of machines. So what's the probability that at any given time at least one machine has failed? That probability is given as 1 minus p to the power n. Okay? As n goes to infinity, this probability goes to 1 because this term starts shrinking. Okay? This is an exponent, so as this exponent keeps growing, this term will shrink, the probability will grow to 1. Okay? So what this is saying is in large systems, as the number of machines grow, some machine being down at any time is the common case, not an uncommon case. So you have to design the system assuming that some number of components will always have failed at any time in a large distributed system. This is not the way you typically design smaller system. In smaller system, you make the simplifying assumption that most components of the system are up, not that some components would have always failed. Yeah, so any large system, this is the case. If you take Google as a good example, the search engine that Google runs on tens or hundreds or thousands of machines. It is probably a given that any given time, some small percentage of those machines are down. They may be down because there's a hardware failure. They may be down because they're down for software maintenance also. They may be updating the OS or whatever. So you have to design it such that let's say 5 to 10% of your machines are always down at any time. So if you put any critical component on a machine, and that machine is taken offline because it's a hardware fault or is down for maintenance, then and that component is not replicated, your system will stop. Okay, so you have to design systems assuming that some components will be down. That means every component has to be replicated. When some component goes down, other components should take over seamlessly and so on. It's a very different way of thinking about how to design your system. Right, so now this is a slightly different perspective of fault tolerance. This is sort of more a computing perspective. Okay? The reason we're talking about this is, or reason we have this entire chapter to think about is the way we have been designing computing systems is very different from way engineers or others design other kinds of systems. Okay? Our software systems always have bugs. Okay? So whether it's operating system or even piece of hardware, they always have bugs, and the assumption is that you will keep fixing bugs. And so crashes are still common. Okay? Although systems are now more reliable, maybe 5 years ago, having to reboot your machine once every 2 to 3 days was very common. Okay? Because something would go wrong and you would say reboot. Right? So that's how people that's how a system was designed, and that's how people got used to it, saying this is fact of life every day. Every other day I might have to reboot because some process has hung or some such thing. Okay? And you could assume that because users of this computing system are tech savvy and they have been trained that every 3 days you have to reboot the system and that's okay, people accepted this. But now you basically have everybody becoming tech savvy. Well, not tech savvy, at least they have the ability to have a network device, whether it's a phone, tablet, or machine. And most common people, I would say, are not used to the fact that you need to reboot your machine every third day. You don't go and reset your car every third day. That's not how automobiles are designed. Okay? They are not designed with bugs that every third day maybe your brakes fail or some such thing and you restart. Okay? So most systems that people use in real life, whether it's a television, your television doesn't need to be reset, your car doesn't need to be reset. So when you give somebody a computer and say every third day you might have to restart it, they'll say why? Why is it designed this way? Okay. So what that also says is the choices we have made in designing computing systems are very different from the way other systems have been engineered. Other systems have been engineered to be highly reliable. Computing systems are not designed to be highly reliable. Okay. As a result, they fail, and they fail frequently. Okay. And this has implications on how users perceive systems. Okay. Now, if your server, so this has lots of problems. Now, as you have lots of people using the internet and there are services that you come to rely on, if any service goes down, people get unhappy. Okay, let's say your banking system online banking goes down because server crashed. Okay. Now people rely on online banking, right? So they cannot access their money, they get upset. Okay, maybe Gmail has gone down often in more recent years. Okay, not often as in every day, but every once in a while you hear news saying 10% of Gmail users basically cannot access their email. People are not used to having systems fail on them. They expect more reliability. Okay, so designing systems to be more reliable has become more crucial. Okay, so the techniques that we are going to talk about, they'll be very basic. Okay, they may not tell you how to design a Google class system to be more reliable, but the takeaway is thinking about reliability is a very critical point when you design your distributors, especially if it's going to be used by lots of users. When users depend on your system, you don't want your system to go down. You want it to stay up, even though some components can fail. Because most users who are not computer scientists do not expect this mode of operation that we are used to or have been used to. Okay, so that's basically the point. So what we want is more dependable systems. Okay, and you can actually quantify this matrix. There is this notion of availability, which a system should be available for a user for any given time. Right? There is something in this literature called 5 nines of availability. So when you hear 5 nines of availability, that basically says it's a 99.999% available. So for 99.999% of the time, your system should be available. That's called 5 nines of availability. If you have 4 nines, that means it's 99.99. Okay. So 5 nines of availability essentially says that your system can be down a few minutes every year. Okay. That's only if you can. If your downtime is limited to maybe less than 5 minutes every year, I believe, that will give you 99.99%, 99% reliability. Okay. So that's the only downtime you can encounter. Okay. 4 nines is, I think, a little more relaxed than that. But that basically says it should be functioning all the time with hardly any downtime. Okay. So that kind of reliability is not very easy to achieve. It is also expensive to achieve. Okay. So we'll study a little bit about what you can do to achieve all of these. Okay. So we'll talk about various forms of failures first. We'll understand what kinds of failures we need to deal with, okay, and what you need to do. Okay, there are some systems that are really critical. Okay, there is a computer system controlling an airplane or computer system controlling a nuclear reactor. As it turns out, airplanes actually run on computers these days. Okay, the pilot doesn't actually steer, he presses a button and there's a computer that does what the button tells him or her to do. Okay? Now, if your computer system is not reliable and your plane doesn't respond to whatever you did, that puts people's lives at risk. So you cannot effectively have, in these kinds of critical systems, you cannot afford to run. So these very special purpose systems don't typically run Linux or Windows. They run special operating systems kernel that have been well tested. Some of them are even formally proven correct. There are proofs to show that this system works as it is supposed to work. It's designed so that they respond in a timely fashion, and so on and so forth. Okay? Now, you don't use those kinds of systems for general purpose use, but for these kinds of mission critical systems, people have designed special purpose operating system kernels and so on that provide you a level of safety and very high degree of availability. Okay? So that's safety. Okay? For most real systems, we will not have that level of safety. A system is not going to be people's lives won't be at risks if banking system goes down. People's jobs may be at risk, but not lives. Different things. Okay? Maintainability says failed system should be easy to repair. If a system goes down, how quickly can you bring it back up? The way, if you design it well that you can quickly repair it, then it is more maintainable than other kinds of systems. So there are many things, many kinds of desirable property. Okay? Now, when you try to design your systems to be reliable, we have to worry about what kinds of faults exist. We will talk about transient fault, intermittent fault, and permanent fault. We have little overtime, so I'm going to quickly show this slide and then stop. Okay? So we'll see that when systems fail in many different ways. Okay? The simplest one is crash failure, where the system simply halts and just stops producing any output. Okay, it crashes. OS has crashed, system has stopped responding whatsoever. That actually, although it sounds bad, is the simplest form of failure. It's actually easy to detect and easy to repair. Okay? As compared to, let's say, a response failure. A response failure is one where the system is continuing to function, but it is producing bad output. Okay? And sometimes you may not know. You query a database saying what's the bank balance, it gives you an output. You assume that the output is right, but if the database is corrupted and you don't know, it is providing essentially garbage, it will cause all sorts of problems. Okay? So response failures where the server response is wrong is a much harder form of failure because the system appears to be functioning. It is producing responses. Okay? Sometimes there are some responses may be right and some may be wrong, and we don't even know what is going on. Okay? So these kinds of bugs or faults are much harder to detect. And then there may be transient bugs. Bugs come and go. Once in a while there is something is going wrong and then bug seems to fix itself. Okay, very hard to even reproduce. If you cannot reproduce the problem, how do you fix it? Or how do you know what went wrong to begin with? Okay? So there are many problems. And the most general one are what are called arbitrary failures. We'll come back to this. They are also called Byzantine failures, which basically says these are the worst kind of faults. The server is doing arbitrary things at arbitrary. So at times it seems to be working fine, but precisely at the wrong time it does the wrong thing and causes problems. Okay? And they are very hard to detect. We will see how to deal with Byzantine faults as well. Okay? So before we delve into fault tolerance, it's good to understand that there are different kinds of failures that can occur. So the simplest one is this machine or system just stops responding, and that actually turns out to be the easiest one. Okay? There are all these more harder problems to deal with where to even detect that there is a failure, there is a problem. Then how do you fix it? Okay, so all these issues we'll come back to. So let's continue next time. Okay, so we'll stop here today.